This is episode 1 of Real Analysis, a History. Calculus, the derivatives and integrals you learned in school, built bridges, aimed cannons, and put people on the moon. It always works. But ever since Newton, nobody could say exactly why it works. Its foundation hides a logical hole simple enough for a middle schooler to catch. Today, how a tiny thing mocked as a ghost stumped the entire math world for 200 years. Let me say something uncomfortable. Your calculus teacher lied to you. So did mine. So did Newton's. And for 150 years, nobody could fix it. 18th century mathematicians had a two-word attitude toward this whole "it works." Narrator's note: it did not work. First, feel how powerful calculus is. Problems mathematicians used to attack separately: the area under a curve, the instantaneous speed of a moving object, how a planet sweeps across its orbit. Calculus handles them all with one toolkit. All through the 1700s, people wrote it at full speed: physics, astronomy, engineering, dead accurate. But it works and I can explain why it works are two different things. And the whole sits right in its most central move: taking a derivative. Let's do the simplest example. The parabola y equals x squared. We want its slope at a point, its derivative. Nudge x to the right by a tiny distance, call it h, and compute the average slope between the 2 points, the rise divided by h. The rise is x plus h, all squared, minus x squared, which expands to 2xh plus h squared. Divide that by h, and the whole ratio becomes 2x plus h. Now let h approach 0, and the derivative is 2 times x. Yes, the answer 2x is correct. But look at those two steps. In step 1, we divided by h, and to divide by something, h must not be 0. In the last step, we said let h go to 0 and erased the leftover h, treating it as 0. The same h, not 0 1 second, 0 the next. The answer is right, but the logic breaks at both ends. That's the famous 0 over 0 move. In 1734, an Irish bishop named Berkeley saw through it. He wasn't trolling, he was a top philosopher with razor-sharp logic. He stared at this thing that's both 0 and not 0, landed a clean blow, and gave it a name that still echoes: the ghosts of departed quantities. One of the most famous theses in the history of math. You might think, what does a priest know about math? But here's the thing, he was right. Berkeley never said calculus gave wrong answers, he attacked its logic. And the smartest minds in Europe, Euler included, couldn't answer him. Their best reply was basically, don't worry about it, it works. When a science gets cornered by an outsider into saying it just works, the foundation really is broken. So how do we fix the hole? The key is simple: we never actually need h to become 0. We only need to know what the ratio is heading toward as h gets smaller and smaller but never reaches 0. Picture a secant line connecting your point and a neighbor a distance h away. As h shrinks, the neighbor slides in and the secant homes in on a tangent line but never truly equals it. The derivative is that target, the limit. Later, Weierstrass nailed the phrase heading toward into a precise language. In plain words, tell me how precise you want it, and I can make it that precise. Throughout, h never has to be 0, the ghost is banished. And the entire subject of real analysis is just reproving every line of calculus in this language. But there's a wilder second road. In the 1960s, a logician named Abraham Robinson had a thought: what if the ghost is actually real? And he proved it. You can build a number system where infinitesimals genuinely live. That subject is called nonstandard analysis. So the same ghost ended up with two homes. On the left, Weierstrass's epsilon delta universe, no infinitesimals allowed, just ask where the ratio is heading, h never 0, ghost banished. On the right, Robinson's hyperreal universe, the infinitesimal dx genuinely exists, it isn't zero, yet it's smaller than every positive number. You honestly compute 2x plus dx, then take an operation called the standard part to wipe off the infinitesimal tail and land back on 2x. Leibniz's old habit of treating dx as a real number was, 3 centuries later, proven correct. It just needed a universe big enough to hold it. Even wilder, this ghost runs inside your phone's AI chip today. Training any neural network means taking derivatives over millions of parameters every step. That's backpropagation. It uses something called dual numbers. Invent a new number, epsilon, with epsilon not 0, but epsilon squared equal to 0. Compute x plus epsilon, all squared, that's x squared, plus 2x times epsilon, plus epsilon squared. Since epsilon squared is 0, the last term vanishes, and the coefficient sitting in front of epsilon is exactly the derivative, 2x. No limits, no approximation, the derivative just falls out. This is the engine under automatic differentiation in PyTorch and JAX. Berkeley's ghost, neither zero nor a finite quantity, is today a line of running code. And derivatives are far more than AI. A derivative is just a rate of change, hiding in things you touch every day. Your car's speedometer shows the instantaneous rate of change of position. Your navigation app's ETA is recomputed from your changing speed. A chemical reaction rate is how fast concentration changes over time. Marginal cost in economics is how much one more unit costs. Radioactive decay, camera autofocus, all the same move, take the rate of change. If those are the present, the real blue ocean is differentiable everything. Differentiable simulation lets robots and drug design simulators learn the optimum themselves. Differentiable rendering, like NERF, reverse engineers a whole 3D world from a few photos. In quant finance, the risk sensitivities, the Greeks, are computed all at once by autodiff. And differentiable science differentiates entire physics pipelines for climate, materials, and fluids. One idea, take the rate of change, is prying open one new industry after another. That's a blue ocean you can enter early. This jump from right to rigorous is the rite of passage for every math major today. Cambridge's analysis course opens by firing 4 soul-searching questions. What exactly are the precise definitions of a limit, a derivative, an integral? Princeton's honors analysis sets the tone in one line. It shows you how mathematicians think about calculus and follows the first 8 chapters of Rudin. MIT's real analysis is, for many, the first time they're asked to write proofs that hold up word for word. All 3 follow the epsilon delta road. The hyperreal road is usually a graduate elective. 2 roads, 1 destination. One line to take away today: being right is not the same as being rigorous. That infinitesimal mocked as a ghost ended up domesticated by 2 parallel universes and became the engine of AI. 3 takeaways. 1. A derivative is the target a ratio heads toward, the limit. 2. The ghost has 2 homes, epsilon delta banishes it, the hyperreals domesticate it. 3. Dual numbers, with epsilon squared equal to 0, put the ghost into AI and open the blue ocean of differentiable everything. Next episode, we meet Euler, a man who tossed infinitesimals around like ordinary numbers, got 1 minus 1 plus 1 minus 1, forever, equals 1/2, and was somehow terrifyingly right. If you like math told as a thriller, like and subscribe for episode 2. That's the whole of episode 1 of Real Analysis, a history.